Alright, we've dealt with decision trees and we defined an impurity function. The impurity function gives us an idea of the quality of our splits as we go down the tree. Next topic that we will tackle will be ensemble learning. Ensemble learning is extremely popular these days. When you go and take a look at Kaggle competitions, you will see that a lot. Yeah. There's two main techniques. One is bagging, one is boosting. Bagging you do when you have a variance or an overfitting issue, and boosting you do when you have a bias or an underfitting issue. What is ensemble learning? Well, basically you combine a set of learners to produce a super learner. Yeah? And I use the example of Francis Galton in 1906. He was a statistician, and there was an ox in a shed, and what he did was he let 800 people go into the shed, come out, and predict the weight of the ox. And to his surprise, when he averaged out these 800 guesses, the final number was quite close to the real weight of the ox. And that's the whole intuition of ensemble learning. So let's start with bagging. Yeah, bagging was invented by Bryman in '96, and it's called bootstrap aggregation. Yeah, I will explain later what it means. Can be used on any classifier with an overfitting or a variance problem, and it can also be used for regression. So let me develop the idea and make an analogy with statistics. So we start from a data set drawn from distribution P that we don't know, and this data set would give rise to a classifier or a model or a hypothesis which we have called H. Let me go back to statistics first, and in statistics we have a few important laws. One is the weak law of large numbers, and one is the central limit theorem. And what do these things do? Well, assume we have a population. We have a population, and a population has an expected value and has a variance. Yeah? And X is a random variable. For example, population could be all Singapore males older than 80. Yeah? Now, how would I calculate the expected value and the variance? I would need to go to every house, measure all the males, and so on. So this is not practical. So statisticians invented sampling. So basically what we do, we're gonna take samples xi. Yeah. Forget about the male and their heights in Singapore. Let's do an experiment. You have an experiment. Yeah, you have an experiment, and the experiment is 100 times 100 coin tosses. Yeah. So the way it's gonna work is you have x1. You do 100 tosses and you count the number of heads. For example, 48 heads. You go x2, do the same thing. Here you end up with 53. And you go until you end up with 100. And in the 100 you have, for example, 49. These are all the people going inside the shed, and they estimate the weight of the ox. Yeah. Now what we're gonna do now is we're gonna calculate the sample mean. Now it's the average of the sample, and basically the number of heads, it's 48 plus 49, and we will divide it by 100 because we've done 100 tosses. So this is your n. Yeah. Okay. Now, what does the weak law of large numbers says? They say that the expected value of the sample mean converges to the expected value of the population, and that will converge to 50%. Right? So this number will converge to 50% when n is large. That's the whole idea. Yeah? Now, this here we could also plot. Yeah? And the central limit theorem says that all these xi's, they are normally distributed, and the expected value is the expected value of the sample mean. Yeah? So your mean will be around 50% when n is high. Yeah? And the variance, yeah, will be the variance of the population divided by n. Yeah? So let us yeah. So these are actually the xi's here. These are actually the xi's, yeah, that you will plot. So the variance of this distribution, yeah, this we also need to call the xi's. Yeah. So the variance is the spread, is the same as the variance of the population, but divided by n. So that's why, of course, you solve your variance problem. The more experiments you do, the lower your variance. Yeah. And the more you converge to the population mean. Yeah. So now let's see how this works with bagging. And in bagging, you're basically going to do exactly the same thing. So we have a data set D drawn from a distribution P, and that gives rise to a classifier. The problem, however, here is that we only have, one data set D. So we need to find an experiment here. We need to find an experiment. So what we're gonna do, we're gonna sample, we're gonna sample from that data set and create the DIs. Yeah? So a DI is a random variable. Yeah? And I can be 100. I can be from 1 to 100. Yeah? So what we do here, we start from our distribution D and we sample with replacement, and that's called bootstrapping. From there, bootstrap aggregation. Once we have the DIs, yeah, we're gonna train the model, and we will get HIs. Yeah, so HI in this case, also a random variable. Yeah. Now, what does the weak law of large numbers say? Well, that the expected value of the sample mean, yeah. So here you're going to calculate the mean, and the mean is 1 over n, the sum of the HIs. Yeah, that's the mean. The expected value of that, so let's call this H bar. Yeah. So the expected value of H bar gives you the expected value of your population. Yeah. If n goes to infinity. Yeah. Or when I goes to infinity. Okay, so we call this the DI here, and I goes from 1 to n. So when n goes to infinity, sorry. Yeah. Okay. So basically what we do is we calculate the average age. Yeah, and the same thing, the variance. Same is true for the variance. So we have here our Gauss curve. This is going to be our HI. You have an expected value, which is called expected value H bar, and that expected value has a variance of the HI equals the variance of H divided by N. Yeah, so it is exactly the same. Yeah, so the only thing we needed to do is, create the DIs from that one data set. Yeah. Okay. Now there's a bit of an issue. Yeah. What is the issue? Well, the issue is the following. These two laws here, they expect that your random variables are IID. Yeah? For one I stands for identically distributed, and the other I stands for independence. Yeah? Now the good news is that they're actually, these DIs are identically distributed and are drawn from the same population P as D. This can be proven, but we won't do it here. The issue is independence. Yeah? The independence condition is not fulfilled. Why? Well, there's going to be some overlap between the D1s and the D. Yeah? Independence means that the execution of one experiment will give you no information whatsoever about the other experiment. Well, once you've done a few Ds, you will get a pretty good idea of what the next D will be. So the independence condition is not met. But random forests and bagging works pretty well. So the results are pretty good. There's a lot of benefits doing bagging. And yeah, this is one of these things where it's more of an art than a science. Yeah. Okay, let's take a look now at bagging on trees. And when we use the bagging technique on decision trees, we have random forests.